Welcome to the International School of Gemology's demonstration on magnetism in gemstones. This concept was first presented to me by Bear Williams, and it's something that I think shows a lot of promise as far as the ability to separate certain gemstones and be able to identify certain gemstones. Certainly this is a very rough demonstration of this, but I think if it was fine-tuned and some better minds than mine got into it, I think it might be interesting to see what came up with this. We have just a styrofoam bowl that I've actually covered in a black plastic so we could see the demonstration better. And this is just a piece of styrofoam that I have cut for the purpose. And we have an industrial grade magnet. And what we're going to do is see if we can find magnetic gemstones. Gemstones that will be attracted to the magnet. And according to the concept is, the stronger the attraction, that can be actually measured and be able to identify the stone. We'll start with a peridot. This little peridot, of course, peridot has a lot of iron in it because it's one of the basic building blocks of a peridot crystal. And peridot having iron, when we put our magnet down to it, it is attracted. We can make it go around the bowl here. Oops, got to be careful not to touch it. But we can make this peridot follow us around the bowl of water because obviously the styrofoam in the water cuts down the friction so that the stone can react and we can actually demonstrate the reaction. But the peridot, as you can see, we can make it move around pretty quickly. Let's go to another stone that has a lot of iron in it, the garnet. This is a nice big garnet. It's about 6 carats or so. We'll put that here, let that water settle just for a minute. And the garnet has a lot of iron in it. We can really make it come around the table. And of course, if we could measure the strength of the attraction to the magnet, we could actually identify the garnet based on magnetism, just like we do refractive index or specific gravity. Very interesting concept. But could we really put this to test now and really find some reactions that would be useful just in the current state? And I actually found that we can. Something very interesting. Rubies and synthetic rubies. Natural rubies will naturally have iron in them. Just part of the crystal structure that most will have. You've got to be careful with your magnet because it'll pick up anything that's metal on the table. Here we have a ruby cabochon. This is about 5 carats. It's a natural ruby. I just barely got it on there, but it's enough. And we can find that this ruby will be attracted. The attraction, of course, is not as strong because there's not as much iron. But there is an attraction, and you can see because I can make it change direction within the bowl of water. So there is an attraction of the ruby to the magnet. And you can see here that I made it stop and turn around and go another direction. Got to be careful not to touch it. But I think that's a demonstration of this. And I do it this way so you can see that we are actually stopping it and making it go another direction to demonstrate that it is being attracted to the magnet. And that's your natural ruby. However, synthetic rubies don't have iron. They don't put iron in just for the fun of it. And as a result, you don't get any attraction to it. So in this case right here, just by this, we can actually demonstrate how we can identify natural from synthetic rubies by use of the magnet. So I thought that would be a fun demonstration and something that would give you pause for thought. Perhaps we're looking at a new type of gemological identification tool by use of the magnet. I appreciate you watching this. I had fun putting it together.